Hi, I'm Joey, and I love playing with toy trains and Arduinos, and so I hope you do too. In this video, I'm gonna talk about AC current, sensing that and detecting trains on Lionel and other toy train layouts. In my last video, I talked a lot about detecting trains, and in particular about using current to do so, but the emphasis was on DC. And so this video focuses on AC and as is relevant to most Lionel train layouts. All right, great. I hope you enjoy this video. Okay, everything we're going to do here today is going to involve the ACS 712 current sensor. It's a Hall effect sensor. It can sense both AC and DC. It's a 5 amp version of this, so it's not horribly sensitive, but we'll see if it's sensitive enough for a toy train layout such as a Lionel. And this is how we're going to wire things up. We've got an ACS 712 wired to the Arduino with ground and power, and we're going to read its value on the analog pin A0. In the circuit of the power supplied to a toy train, that AC current will pass through the ACS 712. As I mentioned before, it doesn't make an electrical connection. It just loops around, and then the ACS 712 detects the magnetic field created by that. So those two circuits are completely separate. So here's what it looks like on the bench. We have our Lionel transformer. That goes to the ACS 712 on one lead. I've connected the A terminal of the transformer to the ACS 712, and then the output from that will go to a train, which is right there on the bench. I also have connected in line with that my multimeter so I can read the amps. And then the ground connects back to the transformer. I just connected it through my connection board for convenience. There's our Arduino Unos back there. And we're displaying everything here in the serial plotter. So you see we're getting at 1.5 amps when the train is going, which is good news, really. We're not in the milliamp range, so this 5 amp sensor should work well for Lionel trains and other toy trains. Okay, we're going to take a look at the sine wave function that we wrote in order to see what the current looks like. Assuming it's AC current, it should be rising and falling at 60 hertz. And so what we need to do here is we want to collect quickly, and display takes time. So we've written it so that it captures or displays. It does not try and do both at the same time. And then it displays just to serial out, and then we'll use the serial plotter to show us the sine wave. And that'll come up here in a second. There we go. And that's with the train off. If we give it some power, we should see AC current rise and fall. That's really good. Now we'll take a look to see how this compares to our multimeter. First we'll go into the code and print out RMS current. And we got a different routine for that, so we just uncomment that, and then we comment the sine wave, and we'll save that, and then compile and load to our Arduino. And once it starts running, we can bring up the serial plotter again, and we'll take a look at what we get, and we'll see how that compares. 0 is pretty close to 0. There's definitely some noise. And then we get this red and orange traces. They separate. The top one is RMS current. The bottom one is peak voltage. In red is peak voltage. So we went full gas and then down. What we did is we went gradually up to full gas and then went down. You could see the current usage was on a slope. Now we went 50%, and then we're going to go to 0, and that'll drop back down. And these numbers are very comparable, and when I look on the values I'm getting, they're very comparable to what the meter says. Now we're putting a magnet near the sensor, and definitely we see that signal we expected because of the magnet. We hooked up a OLED display, and I'll get to that in a second, but when it's displaying RMS current, when the power is off, the multimeter says no current. We were seeing significant current readings, so I took a closer look into that. So in the code, I added a place where we add this offset. This is an offset voltage. And, what I observed, and I made a number of observations and did a linear regression on that, came up with a value. And just empirically, I was finding a value of 0.08 to work a little better in this situation. I later saw it drift some, particularly when it was moved over near my layout where the transformer is. But we got better 0 readings after making that adjustment. And we found the current readings matched up pretty well. There's quite a bit of noise. I'm not doing any averaging here on this one. So if you take the noise into account, these readings are about as close as they could be to one another. So here's how we wired that OLED display. It's a somewhat fancy one, and we used the SPI interface, and it was wired in exactly this way according to instructions. I really didn't have to mess with it at all. All right, well, with some modifications, we can see how this would work on a real Lionel layout. What we've done is we've added an OLED screen so the project can be moved around a little. Otherwise, it's the same. We've wired into the line leading to one block of electrically isolated track. If you see here, this switch, this center rail is not connected to the other center rails. It does connect to that green wire. And that green wire comes up here and would normally be connected to this relay. And that relay, when it's active, provides power to that siding right here. So we can turn that off and there's no power. And we get about a 0 reading. I just turned it back on. It's right here is the indicator light. And we still have virtually no power. We have a train on the siding. So if we then come over here to the throttle and we'll throw some juice on. The train is moving a little. And we had seen 1.3 amps. I had to stop it because we got to the end. But here we are. We're in neutral. All right, so here's our train. Stopped toward the end of the siding. And here's our reading, which is 250 milliamps or so. If I increase the throttle, that goes up. The light on the engine got brighter. This makes sense. We're using a little more energy. And now we'll go forward. So here comes the train. And we're getting toward 2 amps. And then it's suddenly, the train's still going. I just moved it to neutral. But you notice we've dropped back down to toward 0 amps. Okay, so here's an illustration. You notice we've got about 100 milliamps, 150 milliamps, somewhere in there. And the reason we have that is I moved the experimental block, and put it on top of the transformer. So the magnetic field given off by the transformer is, worth over 100 milliamps. And those differences can be significant. You want to be able to set a threshold for when your trains are standing with power, and maybe another threshold for when they're running. But you certainly want to know a train is on a siding, even if it's standing with power. As I illustrated, you can't really tell if power is off to the train, whether it's there or not, using a current sensor, or using this current sensor on an AC layout. So we did some more wiring. We wired up a switch, and we wired up an LED. That's in the upper left of the diagram. Otherwise, the wiring is the same. And then we also wrote a little more code. All right, well, so now that we have the OLED screen, we can say whether the train is on the siding or not. There it says, I'm away. We also have added an LED that lights up when it's on the siding. And we added a switch, which I'll utilize later. You'll see how that works. But there's our train. And we're going to head to this siding, to which this, the current sensor, the Hall effect ACS 712, is connected. And so let's power her up. I'm home. And we're sitting here parked, and it knows we're parked. And if we move, get more amps. But here's the thing. If we turn the power off, right, it goes effectively to 0, which, to be clear, so there's the train. It's outside of the siding, and we have, roughly 0 amps. Okay, here's the train on the siding, and we have 0.2 of an amp. Okay, that's in neutral. But if we kill the power, we have roughly 0 amps. So you can't tell the difference between a train that's off and a train that's away from the siding. And then there's another little bit of fun we can have with this switch. Since we had since I wired this up, I thought we might as well get a little AC current display action. So this is parked. It's so little current that our display doesn't look so good. But we can crawl to a stop more or less. So with the motors powered, we see We have an AC signal. It's at 60 hertz, just as we expect. So that's all good. Everything is as it should be. Okay, before we get to the summary, I just want to revisit the zero offset. That having that zero offset definitely affected the low end and made it hard to set thresholds for trains that are standing in neutral and off or off the siding. And so I took a closer look at that, made some measurements, did a linear regression, and found the intercept. I found this method worked pretty well, and even though I had a little bit of drift and didn't use this right away, I ended up using it in the final. And the only thing I can say is that the electrical offset voltage and the quiescent output voltage descriptions in the spec sheet, the data sheet for the device, give us clues that this is something that you have to deal with. And so we've dealt with that in this way. It's more significant than the data sheet indicates it should be. So I'm not sure exactly what's going on there. I think it is what it is. But we could handle it by applying this factor. Okay, let's get down to brass tacks. Let's face it, what we really care about is detecting our trains. And so we want the readings to be consistent, and we want there to be a difference so we can tell if a train is stopped with the power on, running, or not present, or perhaps just turned off. It would be nice to be able to tell the difference between those latter two, but there's no way that this sensor can do that. We care about simplicity, and we care about ease of installation. So how did the ACS 712 stack up? Well, I'd say it's a mixed result. Certainly it had enough sensitivity to tell the difference between a train running and stopped, and it probably has enough sensitivity to tell the difference between a train that is off and standing with power on. But that all depends on how good you correct for the baseline threshold and how stable that is. If it changes over time, say months, then the thresholds you're set would have to also change. So for that reason, the tricky part might be setting those thresholds. But it's a simple device. It just wires to the Arduino to an analog pin and power. And we can install it anywhere along the wires that feed the power to any siding. We might just not put it right up against the transformer or right up against the track. Okay, I decided to do a quick run through of how my trains perform in this situation. I set a threshold of 0.16 amps. So anything above that will mean the train is present. And what I did is I took each train, pulled it up to where it's next to the OLED readout and the multimeter readout. So you can compare those two numbers as well as see what train we're measuring. So I'm just going to run through a series of these photos really quickly. Just a note on this one, our current matches up pretty well. I think what we're going to see is the current difference between the multimeter and what we get from the ACS 712 is pretty consistent except for digitally equipped trains. So keep an eye out for that. Okay, thanks a lot for watching. If you are using current to detect your trains, particularly if they're toy trains running on AC current, please let me know. I'd like to hear about your experiences. And as always, don't forget to like and subscribe.